Video number 5 of this chapter. We are covering kind of 3 different sections in our book, but we're going to pull them all together and refer to them all as very similar shapes to each other because they are all related to circles, and that is what our whole chapter is on, is related to circles. Now, previously we have been doing circumference and area of circles, and now we're going to start to focus on how circles can be incorporated into more three-dimensional objects. So this is why we are going to now discuss cylinders, cones, and spheres. So first we're going to focus on the cylinder, and a cylinder really has two main pieces to it. It has a radius and it has a height. Notice I'm using a capital H to refer to height because a lot of the times when we were referring to two-dimensional objects, for example, like, a rectangle, let's say, we had base times height. Well, the height two-dimensionally and the height three-dimensionally are kind of two different things. So anytime you see me refer to the height as a capital H, that means that the height is three-dimensional. And if I'm using a lowercase h, then that height is meant to be more for a two-dimensional or more for a flat object. Now, the top and bottom faces, or what we will call bases, of a cylinder are made up of what shapes? Well, they're made up of, circles, right? And what is area of circles? Because keep in mind, we want to find the surface area of a cylinder. That's going to be our whole goal here, is to find the surface area of cylinders, cones, and spheres. So if we break down a cylinder, well, there are two circles, top and bottom, and the area of circles is pi r squared, just like it was last week. So we've got that, right? We know this is going to be pi r squared on top. We're going to have another pi r squared on bottom. So altogether we have, what, 2 pi r squareds that make up the top and bottom circular bases. Now we just need to talk about this middle part, okay? And in years past, I have seen that many students know what this will unroll out to be, if you will. So imagine this is like a roll of paper towels, if you will, or toilet paper. And if you were to unroll a piece of paper towel or toilet paper, and you were to flatten it out, what shape would it basically unroll out to be? Well, it would be just a rectangle, right? And, this is called a net whenever we take our three-dimensional shape and flatten it out. It kind of looks like an old school division symbol, right? But here's, kind of our top and our bottom circles. But we're trying to focus primarily on this rectangle at this point. What would be, at this point, the area of this rectangle? Okay, and this is called, as I have here, it's called the lateral face. So this piece, it's kind of like the wall, if you will. It's called the lateral face or the lateral area. How would we find the area of this rectangle? Well, you might say, well, rectangles are base times height, so it's just base times height. But we don't really use base and height in this cylinder, though. We use height, though, right? So let's talk about, if this represents the radius and this represents the height of our cylinder, well, then the height of the cylinder is still technically the height of this rectangle. Okay, but it's the capital H, if you will. But now we need to talk about, well, what's the base of this rectangle? How is that related to the cylinder? Well, this part on the bottom, this is the part that would, right, this part right here, let's take half of this. This piece would wrap around and be half of the circle, right? This piece would really wrap around to there. And then this other piece, the right side over here, it would wrap around the other side of our circle. So what's that called when we go on the outside part of a circle? What's that length called? Well, that would be the circumference, right? It's full circumference even. So the base of our rectangle here is nothing more than the circumference of one of the circular bases. Okay, so our lateral area, whoop, this is kind of crazy. Whoop, whoop, let's back step here. Do. There we go, that's a little better. There we go. Okay. The lateral area, or the lateral face, it's really a rectangle, and the base, if you will, base times height of that rectangle is really the circumference, we said, times the height of the cylinder, which is really like the height of our rectangle. And to put it into better terms, the circumference was pi times d. Okay, so the c is this part, pi times d, and the h is the h. Okay, so if we want to make those capital H's, we certainly could. Let me get a different color here. Let's go there. There we go. Make that a capital H. So now what we need to do is to put all of our pieces together. Okay, because cylinders are made up of three pieces. We got the top, we got the middle, we got the bottom. If we want to find surface area, we need to find the sum of all of the surfaces of our shape. Okay, so let's put it all together. The surface area is really two bases plus the lateral area. Okay, and our two bases are nothing more than two circles. And each circle is pi r squared, and so I put a 2 out in front because I have two of them. And then we just talked about that the lateral area was pi times the diameter times the height. Okay, so here is our handy dandy formula. You could talk about this formula in other ways. For example, I'm just going to throw this out here to show you how we could really simplify things. Instead of a d, we could talk about a diameter is 2 radii. And then we could even go crazy here because both of these two pieces have a 2 pi r in common, right? So we could factor out 2 pi r. What would be left from this? Well, we'd still have a leftover r, and what would be left over here would just be an h. Ooh, now we can go even crazier. Get ready for this. What's another way of talking about 2 pi r? Well, 2r was really a diameter, so this is really like saying pi times diameter, which is the circumference. So we could even break this thing down into the circumference times the radius plus the height. Okay? This is the way I think of the surface area of a cylinder, because I see two circles plus, then this is the lateral part. Okay? If you want to use, and you certainly may, use this newfangled, oh, if I can press the right buttons here, there we go. If you want to think of the surface area of a cylinder as the circumference times the sum of the radius and the height, you certainly could. That's fine. But you don't really see the two circles and the that rolled up rectangle in the formula with this. But either way you want to use it is fine with me. Now, one last thing to talk about before we proceed on. When we talk about surface area, and you might want to make a little note of this in your notes, no pun intended, is the surface area means any surface you can touch. If you can't touch a particular part because it's inside, contained inside something, then you don't include it as part of the surface area. Okay? So any surface you could touch, or think about it as any surface you could paint. Okay? So the first example. If the surface area of a cylinder is 130 pi, and the height is 8, what is the radius? Okay, so we have a problem here where there's no picture involved. We do have numbers, so we can't make up numbers like we could with our probability questions earlier. So I've been given information about the surface area. Basically, I know the answer is 130 pi, and I know the height used to get the 130 pi is 8. I just need to know what is the radius. Well, problems like this are going to be more algebraic in nature because we have to do them backwards, essentially. And we need to figure out what is the algebra that gave us the 130 pi. Well, what I would start with is, well, what is the surface area formula? And so I'm going to start with the formula that I said I would use more, that I can see my two circles plus the lateral area part, that rectangle that gets rolled up. And now I just plug in, well, I'm just going to plug in, if I can get this going here, plug in everything that I know to be true about this formula. For example, I know the surface area they told me is 130 pi. The radius, that's what I'm figuring out. So this has got to stay r squared. Pi times the diameter, Well, here's what I'm going to do. I'm going to convert the d into 2r's, okay? Because I want to know what the radius is. So I need to make all the same variable, right? It wouldn't make sense to have a radius and then a diameter when there's really a relationship between the radius and the diameter. And then I was told that the height is 8. So let's clean this up here. This is really 130 pi equals 2 pi r squared. I couldn't really do anything with that. But this part over here, well, I can take the 2 times the 8, and that's 16 pi r. Perfect. All right. Now, is there anything else I can clean up in here? Well, I've got 3 terms going on here, right? And hey, you know what? They all have a pi in common, right? So what if I divided pi by everything? What if I divided this by pi, and this by pi, and this by pi? Boom, boom, boom. Pi's are all gone. Now you might ask, well, what about that plus sign? Isn't that junk? Am I allowed to just cancel that out over here? Yeah, because technically this is what we're really doing, if you want to think of it this way. Really, I'm going to factor out the pi from these 2 terms, and I'd have 2r squared plus 16r, and now I can think about this as dividing both sides by pi, and so it looks like that. I get the same result in the end, okay? Just make sure if you're dividing on both sides, that you're really dividing each little split up part by plus or minuses by the same thing. Okay, I couldn't just pick on this pi and say, well, I want to divide it out, but leave this one and the 16 pi r there. You can't do that. It's either everything or nothing. So now let's get some space in here. Okay, so our pi's are gone. That's nice. We don't have to deal with pi anymore. And I really don't need those parentheses anymore, so I'm just going to get rid of them. And then what else do we have in common? We had the pi's in common. With 132 and 16, there's a common factor of 2, right? So I can think of factoring out a 2, and then I'd have r squared plus 8r, and then I can divide both sides by 2, and then I'd have 65 equals 8 squared plus 8r. And then this is where some of you might start doing some math magic. You might look at both of those things and go, well, hey, look, both of those have an r in common, so why not factor out the r and then set both the r and the r plus 8 equal to 65? But that's not the way the factoring works, okay? We have a square term, we have a not square term, and we have a constant. We have done these problems time and time and time again. This is a factoring problem, except we need to do one little thing first. We need to move everything over to the same side. So I'm going to move the 65 over to the right. And so I have 0 equals r squared plus 8r minus 65. Okay, now since my r squared really has a 1 in front of it, this is going to be the easier type of factoring. So I already know I can set this thing up as r and something times r and something, because that's the only way I'm going to get r squared is if I have r times r when I think of foiling or double distributing. Now I need 2 numbers that multiply to be negative 65, but at the same time add to be positive 8. So I need to start thinking of what numbers multiply to be 65. Well, 1 and 65, but there's no way I'm going to get 8 out of that if I add those. 5 can go into 65. How many times? Let's see. 13. And I need a negative 65, so one of these needs to be negative, either the 5 or the 13. And in any way, if I add these, will I get positive 8? Yeah, this combination will give me positive 8 when I add them together. So those are my 2 numbers I want. I want radius minus 5 and radius plus 13. And now this is the point where I can take each one of my parentheses and set them equal to 0 and solve. So I get radius equals 5 or radius equals negative 13. Now, we don't just stop there. We've got to think, can I really have a cylinder that has a radius of negative 13? No, we cannot. That was called, once again, an extraneous solution. And so our truly only algebraic and geometric answer here is that this must have a radius of 5. Okay, so factoring's still going to play a role in this chapter. The second example, I'm going to have you guys do, but I'm going to help you visualize this first. Because I know if I just leave it at that, you will have no idea what's going on here. So, it says, imagine this rectangle being rotated around the y-axis. Calculate the surface area of the resulting shape. Now, the y-axis is the vertical axis here. So we're really going to take this rectangle, and if you will, we're going to swing it around. You got to think of this kind of three-dimensionally now, that this rectangle's just swinging around. Okay, it's like, think of an example here, kind of like a merry-go-round. Okay, it's really just going to be spinning round and round and round and round and round. So here's what we can kind of think of. And I think I marked this on your papers of your notes, because it might be kind of hard to see this grid back here, but you could easily see it in the video. This has a length of 5 units, and this has a length of 7 units. Okay, so when this rectangle starts wrapping around this side, and then it's going to wrap around back to this side, well, really, we're just going to see another rectangle that's the same size over here on the left side of the y-axis, right? So we're going to see another rectangle come over here. And you might look at this and go, all right, well, now I have kind of 2 rectangles, or a rectangle that's twice as big as what it was before. How does that really help me? Well, here's what you need to think about the three-dimensional part that's happening. This top right corner right here, okay, as it's spinning around, it ends up being this top left corner. And then as it continues the rotation, it comes back to this point. So what type of shape are we making up here? We're making a circular motion, a circle up here. And what's going to happen down here in this bottom right corner? Well, it's going to be wrapping behind and then wrapping around in the front. So think of this thing as a cylinder. Okay, this is kind of the front, if you will. I'll try to make this thing look a little more solid here. I've really got a cylinder. Okay, here's my top of my cylinder. It's a circle. There is a bottom part of it down here that is also a circle. Okay, so let's briefly, I'm not really going to give you too much wiggle room here and give away the answer, but think about, what does the 7 represent in our cylinder? What does the 5 represent in our cylinder? And now you guys can tackle